despite the fact that I was stressed out constantly when I was there, and I thought every day that it was my last day. Actually, I was just advising a student here who's going to try to transfer to Princeton from here. She knows it's a long shot, she knows it's hard, but she's going to go for it. Mm. And I gave her the best possible advice.
Yeah, so, well, it's to go with a strategy, right? And trying just to...
Well, I had no strategy. My strategy was to...
Estamos aquí en ACR. Esta entrevista va a ser en inglés. Voy a poner subtítulos para que sea más fácil de entender, pero bueno, I hope you will enjoy it. I definitely think so, because today we have Professor Frank here. Professor, can you tell us a little bit about yourself?
Sure. So, yeah, my name is Frank. I'm a doctor of physics, astrophysics in particular. I got my PhD from Syracuse University in 2020. I got my Bachelor's of Science from Columbia University in 2013. And I started out at Ocean County Community College, and I got my degree, my associates in mathematics there from 2008. And I like to play music. I am very passionate about physics and physics education. And yeah, that's pretty much me.
Interesting. How did you decide to study physics?
I was always interested in it as a kid, but I didn't have the best grades in mathematics. And I struggled with math a lot, and I thought, well, this isn't for me. So I was really big into English in high school and stuff, when I was still kind of coming of age. And then in my 20s, I was doing other jobs. I was working in film and radio and these creative forms of writing and performing, and I just realized it wasn't satisfying me. And I was still reading physics books and thinking about physics, and I thought, you know what, enough. So I just plucked up the courage and I went for it. And so that's why I went to community college, because I knew at the age of 24 I was a little green when it came to math, and I was never a big math student, before that. So I knew I had a lot of ground to make up for. So I just went to Ocean County Community College, and I hustled, and I just got all my math skills up to par, and I took my time. Took a couple extra years just to get acclimated and make sure that I liked it, that I really wanted to do it. And I did. And I did so well at Ocean County Community College that I became a tutor there. And that was just more affirmation that I should do this. So I did. And then when Columbia happened, I got there. As you would say, the dam was just broken open. And it couldn't stop me after that. So that's what caused me to get into it. Just a self-awareness that I wasn't happy with what I was doing. I wanted more. I wanted a deeper connection to nature. And I just needed to stop being so afraid of it and just go for it.
Oh, wow. A couple of times during lecture, you mentioned a professor, right, that inspired you. What people inspired you to pursue your passion about physics?
Well, at Ocean County Community College, there was a couple of professors. There was a physics professor who was an engineer, a retired engineer by the name of Neil Schiller. And he was a mentor of mine, wonderful man. Just let me hang out in his office, and we would talk about class. We'd also talk about just philosophy in general, like what makes a good experiment, what makes a good theory, Einstein, and just general pontification. So he was a wonderful man that pushed me to do it. It made me feel like if I could get on with this person, then maybe I'm one of these people. There was another professor, he was a math professor, he taught differential equations and calculus. His name was Theodore Gordon. He was a brilliant professor, just one of these professors that just made it look so easy. And he's just so good. And he really helped me with my math skills, the higher level math skills, differential equations, Calc 3, Calc 2. And then at Columbia, there was a couple professors too. There was a professor by the name of Brian Humensky, who I did undergraduate research with. It was called the Veritas Group. So where you look at the energetic radiation that comes in, cosmic rays that come in from outer space, and you measure them to try and learn more about the universe and black holes and so forth. And there was another professor at Columbia College by the name of Eric Weinberg. He was my quantum mechanics professor, and I performed atrociously on his midterm, and I really beat myself up for it. And I went to go visit him in his office, and he sat, and this guy, he's very established. He has got a Wikipedia page. He discovered something called the Weinberg potential. This guy did not need to do this, but he just let me hang out in his office, and he went through the exam, and he pointed out where I went wrong, and I took his notes, and I went home, and I redid the exam at home. I figured out everything I did wrong. I perfected my study habits. I knocked the final exam of that class out of the park, so I got a good grade in the class, and he wrote me a letter of recommendation for my graduate school application. So
Whoa.
yeah, so a big win, a big sort of rising from the ashes kind of moment there,
Ooh.
which is all part of the college journey. So those were some people.
Whoa, I didn't know the whole story. It's interesting to know about these special professors, right, that are really interested on teaching people and caring of students. Do you have like mathematicians or scientists that are your idols also?
Sure. Feynman. I love Richard Feynman because he was not only a brilliant scientist, but also he was a brilliant educator and communicator of science. He was very accomplished and high level, but he knew how to speak about science in a way that it was accessible to really anyone, which falls in line with Einstein, and my next, favorite, because Einstein believed that any a good physics theory should be able to be understood by everybody on some level. Maybe not. Maybe they don't understand every little subtlety and nuance of it, but they should understand it on some basic fundamental level, because physics is nature, and we are nature. So it's not this inaccessible thing, and people shouldn't be afraid of it. Yes, it's difficult. Yes, it can be stressful, but it's the best kind of difficult. It's the best kind of stress. It's beautiful. It's rewarding, and it transforms the way you view the world.
Yeah, but unfortunately, sometimes high school or some different educational systems make it quite difficult to go through, right? So
yeah, or there's this feeling of physics, that's not for me. I can't do that. That's for smart people. And I think that's nonsense, quite frankly. No pun intended. I think that is ridiculous. Physics belongs to everyone. There was a time, in the 1700s, 1800s, when the study of physics, calculus, and so forth was reserved for the privileged and the rich, because everyone else was too busy surviving, and that is terrible. That's a crime. We should not go back to those days ever.
No, I have a question, Professor.
Yes.
So let's imagine that you're a director of a high school. What would you do to promote this physics, about curiosity about physics or math career?
A high school? Well, I have no desire to be anything at a high school.
But let's.
But I'll tell you this: I have a niece who's in high school, and she's very smart. She's in a lot of high-level classes, and she's always telling me very proudly of all the things she's doing. And she said, "I'm taking chemistry." And I asked her, "Did you take physics yet?" And she's like, "No, that's not till later." And I'm like, "Why? Physics came before chemistry." So if I were in charge, if I had my way, I would push all the other sciences, chemistry, biology, to the side, and I'd make physics the most important thing for students to learn.
Because it's the basics, right?
Not the basics, but it's the first principles. It's the foundation for all other sciences, and that's not to say that it's easy. It's just, and if anything, that's quite the opposite. it's quite involved. For example, when you first learned chemistry, you're looking at tables and lists and charts. You're looking up numbers all the time. In physics, you start with Newton's second law, force equals mass times acceleration. Or as I say, the sum of the external forces acting on an object is equal to the mass of that object multiplied by the acceleration of that object. And you take it from there. And if you're going to do a bit of calculus, maybe you say acceleration is the second derivative of position with respect to time. And, so forth and so on. So you start from a first principle and you work your way outwards to these bigger ideas. And eventually, if you are really thorough, you can get to those results on those tables and charts that you see in chemistry. So, yes, it's everything. And the great thing about physics too is, it teaches you how to think. You'll never look at a problem in your life the same ever again, even if it's not a physics problem, it's not a science problem, it's just a personal problem or a political problem or a familial problem. You won't look at it the same. You'll be a problem solver. And you'll be able to logically deduce and think and work stuff out, and it will make you stronger for the better in the long run. I guess any intellectual pursuit will do that, but I feel like physics is the strongest. I mean, you could do it with English if you want. You could just read a bunch of novels and like brilliant novelists, and that could help you grow intellectually. But I just feel like physics it's everywhere. It's the end all be all, and it was here first and it will be here last.
Yes, definitely. Oh, wow, interesting. Please take note.
Yes, there will be a test at the end of this interview.
Yes. Another question that some friends wanted to ask you is about your career path and specifically how did you get to Columbia? We know it's hard, quite controversial. So, would you recommend high school students to try to apply to Ivy League schools?
Sure, absolutely, yes. I loved my experience at Columbia. It was extremely stressful.
How?
It was just a lot of work, and I was constantly afraid of flunking, just like everyone is who goes to Columbia. And that's the reason why I did so well, because I was always on my game. But it's funny, while I was there, I was miserable. I was working so hard, I was so tired, but I was growing. I could feel myself growing, and I wouldn't trade that experience at Columbia for the world. They, for example, not only do they have a brilliant physics program, of course, they've got Nobel Prize winning people as professors, teachers, but even their liberal arts programs, all their English programs, their writing programs that have nothing to do with science are brilliant. I took this one course, it was Shakespeare, and we went to go see Shakespeare in the park, and we saw the Royal Shakespeare Company do a couple performances, and it was such a great class, such talented people there. So I say yes, go for it. Tricky bit is, if you don't go into Columbia from high school, which is known as the traditional path, the only way to transfer in is through the School of General Studies. Now, if you are accepted through the School of General Studies, it's just as tough to get in as it would be to get into the traditional route, and you still take the same courses. So you might wonder why they do this, and I don't really have a good reason for it, other than it's just what they do. And they can do it, they can get away with it because they're Columbia. But that's it. And so even if you don't go to an Ivy League school straight out of high school, there are ways to transfer in. Actually, I was just advising a student here who's going to try to transfer to Princeton from here. She knows it's a long shot, she knows it's hard, but she's going to go for it. Mm. And I gave her the best possible advice.
Yeah, so, well, it's to go with a strategy, right? And trying just to...
Well, I had no strategy. My strategy was to learn as much physics as I possibly could, and math to help me learn physics as much as I could. I just did it for the sake of doing it, and everything else just happened the way it was. Mm-hmm. I think I think Columbia saw in my application someone who was passionate about physics, someone who maybe started off a little rocky coming out of high school, but found their groove. They gave me a chance, and it paid off. I ended up graduating magna cum laude. So I not only made it, but I made it with honors, despite the fact that I was stressed out constantly when I was there, and I thought every day that it was my last day. You know, as a student, you know, it was like a bit of a psychosis. It's not uncommon at that school.
It's a shame, but
well, there can't be all roses all the time, right? Sometimes there's a necessary pain to bring pleasure.
Well, talking about your experience, at this point of the interview, we know that you love physics. So, changing a little bit the topic to physics, could you explain us why physics is so important in real life?
Well, as we said before, it's the foundation for all other sciences. It is based in philosophy. It's all based on first principles, so it's very thorough. It's as complete as it possibly could be as a science, and it gives you a great mindset for problem solving and thinking. So, yeah.
Interesting. Well, the next question is, what aspects of physics do you find more interesting for you or more engaging?
I would say it's gonna be a terrible answer, but all of it, because it's all connected. So, for example, this question of dark energy. Dark energy is causing the accelerated expansion of our universe. It's going to be the end of this universe. Dark matter. These questions. That's obviously very interesting, and it's very topical. It's very now. However, Newton's laws are, or just, you know, how a block slides across the table is just as interesting to me. To think about, you know, friction, for example, the electrostatic forces at work, and why that occurs. Or to think about a universe without friction. That is a universe where nothing's touching. Everything's separated, and that's where we're heading with dark energy. So you see, it all comes around, and that's what makes physics so satisfying in that way. It's so complete. It's so thorough.
And until scientists discovered difficult topics like quantum mechanics, right? Could you explain us a little bit about what's quantum mechanics and why it's so confusing?
Sure. So, it all started with the discovery that light was an electromagnetic wave. It's a changing electric field and a changing magnetic field constantly inducing one another, which manifests itself as electromagnetic radiation. Then the question became, well, if light is a wave, then what medium does it travel through? Because the logic was that waves need a medium. Water waves need water, sound waves need air or gas, or even a solid. So there's this question. And the answer was that light propagates through a vacuum, a perfect vacuum with nothing in it. It doesn't need a medium. So there was this moment of, well, how can that be? So we studied light a little bit more, and we studied the thermal radiation coming off a black body. That is a body that absorbs all radiation that it interacts with. It doesn't reflect anything, and as a result, it gains energy and its temperature changes, and it emits thermal radiation. And we analyzed that light, and we saw that it did not follow our classical predictions of light. So, okay, what's going on with light? Light is so special. Light is so interesting. And then it turned out that to explain this phenomenon was to discover and realize that light is both a particle and a wave at the same time. There's a duality to it. And that was discovered by Max Planck. that was black body radiation. And then it was confirmed by Einstein with his work on photoelectric effect, which is the effect of when light strikes a metal, it will actually, liberate electrons. So they were able to confirm that light is indeed both a particle and a wave. So that was the birth of quantum mechanics, the duality of light. And then this led to the discovery of something called the de Broglie wavelength, which is that not only is light a particle and a wave, but things that we thought were particles, like electrons, are actually a wave too. And as a matter of fact, everything is a particle and a wave at the same time. I'm a particle and a wave. You're a particle and a wave.
Depending on the perspective, right? As you said in class the other day.
Now, as far as the why or the how of quantum mechanics, there's no answer to it. No one really knows. There's different interpretations of quantum mechanics, and for example, there's something called the Copenhagen interpretation. That interpretation says that things are a wave until you observe them, and then the wave collapses into a particle. There's another idea called the many worlds theorem, which is things are a wave and they follow something called the Schrödinger equation. And there are an infinite number of realities where an infinite number of things can happen. And that's another theory. And there's some other ones as well. There's one that says that something along the lines of you have a wave, a quantum wave that describes the entire universe. Of course, in the universe, there's different parts of the universe that experience stronger gravitational forces than others. So the wave will experience different gravitational forces, and that will cause collapse of the wave in certain areas. And that's sort of, now we're getting into a little bit on quantum gravity. I'm being careful about how I'm speaking about this because I haven't really done a deep dive into the research on this in a while, so I don't want to say something that's blatantly wrong. I'm just giving you a general overview. My point is, reciting all this, is just to tell you that no one has quantum mechanics figured out. And as a matter of fact, Niels Bohr was famously said that if anyone thinks they understand quantum mechanics, they don't understand quantum mechanics.
So, how people study quantum mechanics at college, for example, or at graduate school?
Well,
do you explore the theories, or
you can work with something called qubits, which is quantum computing. You can do quantum mechanics experiments. You can do a photoelectric experiment. I ran one at Syracuse for upper level undergraduate students. It was like the last few semesters of their physics curriculum. They did some high-level experiments. They did the photoelectric effect. So, yeah. And we're actually hoping to get a photoelectric effect experiment as well as a black body experiment here at the college at Atlantic Cape.
Wow, interesting. We're about to talk about the physics program, but the last question is, you're an astrophysics, right? And what nowadays studying astrophysics, or what would you like to discover these?
Well, my specialty was in the formation of life-essential complex organic molecules on dust grains in outer space, and how that can seed planetary life, or when those dust grains eventually all collapse into a planet or a star, and stellar evolution. So with the James Webb Telescope now, we're getting really interesting data regarding galaxies, nearby galaxies, and we're starting to see some interesting data on that front. So that's something I'm interested in, but I'm also really interested in gravitational wave astronomy. That was not experimentally proven until 2015. It was a prediction of Einstein's theory of general relativity. And even Einstein said, I don't think this will ever be experimentally verified because the distortions of space-time, which are gravitational waves, are so small and so hard to measure that he couldn't imagine the technology, to capture that phenomenon and confirm it. But we did it. We did it in 2015, and we're doing it more and more now. We're actually and all our our interferometers, our gravitational interferometers, are all on the surface of the Earth, which is inconvenient because the Earth is very noisy and vibrational. So they're actually talking about something called LISA. It's a project called LISA, which is a gravitational wave interferometer that would be in space. So.
Oh.
Yeah.
Well, interesting. I didn't know that last part.
Mm-hmm.
Oh. So.
That's definitely very astrophysics.
Yes, my mind is exploding right now, but.
Physics will do that. It's okay.
And for that, we need more people interested on studying physics, right?
Yeah.
So, to talk about more your physics program here, could you tell us as much as you can about your program? Is it possible?
It would be Associate's of Science in Physics. It would be essentially the first 2 years of a Physics Bachelor's of Science degree. The central goal of it is to give students the best possible physics foundation we can here at Atlantic Cape. And it would be special because you really don't see this very often at community colleges. You see biology, you see chemistry. You don't often see physics. And it's about time we had it. Poor physicists are usually pushed into math or engineering. And physics is not math, it's not engineering. Physics is physics.
How could you describe the difference between math and physics, for example?
So math is purely abstract. Math is an abstract, logical language that us very involved chimpanzees invented. It's a miracle it works in describing nature. It's brilliant, it's beautiful, but math by itself is abstract. And that's fine. That's fine. Actually, that's very useful with regard to encryption. Encryption, you build these little sort of mathematical universes that have millions of dimensions to them. And you can do that with pure abstract math, but you can't quite do that with physics. The idea of playing with the dimensions of nature. We're very careful about how we define dimensions of nature. We can think about space having 3 dimensions, time being a dimension, so there's 4. And if you were to think about things such as string theory, it's predicted that there's up to 11 dimensions of just all curled up on top of each other.
What?
And that's at something called the Planck scale. So that's at a scale at which we are unable to experimentally verify anything. But that could change. I don't know how. I'm not a string theorist, and I'll admit right now I'm not too well versed in it. But it's very interesting. And Einstein was working on it on his deathbed, so it can't be that bad.
Well, thank you, Professor. And what new courses will integrate this new physics program to ACCC?
So currently we have our physics courses are on the calculus level is General Physics 1 and 2. Mm-hmm. And you pretty much stop at electromagnetic radiation. And you don't really give Maxwell's equations a good look. You don't really study the wave-particle duality of light. There isn't a good treatment for geometric optics, fluids, or thermodynamics. It's touched on in college physics, which is for non-science majors. It's a non-calculus based lower level, but it's not really given a good treatment on the calculus level. So what we're hoping to do is to introduce 2 new courses: General Physics 3 and Introduction to Modern Physics. General Physics 3 will cover fluids, thermodynamics, and geometric optics. So we'll fill those holes that we currently kind of have, which will be good because you need that in your first 2 years as a physics student at a 4-year school. And then Introduction to Modern Physics will be a capstone course, meaning it will be purposely light, but still nonetheless interesting. And it's just meant to introduce the student to modern physics, just kind of tell the story of what happened, sort of like I just did with Maxwell's equations and black body radiation and photoelectric effect and the de Broglie wavelength. We'll kind of walk the student through that in a very friendly, introductory way, such that when they see it, when they transfer in a much more rigorous form, we'll have at least seen it before. And we're going to do our best to give it the most diligent and thorough treatment we can without, overstepping, because, there's sort of like the way I think of it, it's like community college is a little planet, and when you leave community college and transfer, it's like you gotta break the gravitational pull. You gotta get through the atmosphere, and an introduction to modern physics is like the stratosphere. It's sort of like it's not our responsibility to give you a thorough, rigorous modern physics course, but it is our responsibility to at least tell you what's coming up, saying you're about to leave the planet, you're at the brink of the stratosphere, good for you. Before you go, here's some stuff that you're going to see, and it's going to be very tricky and strange and lovely. So we're going to introduce it to you. And so that's Introduction to Modern Physics, which I'm thrilled for. So, like, for example, if we, we're going to get a black body, we're hoping to get a black body radiation and photoelectric experiment. So if we can have students do those two experiments, right there, you're already off to a running start for your proper, rigorous modern physics course. Mm-hmm. If you can do those experiments and see that phenomenon firsthand, do those calculations, which are surprisingly not difficult, believe it or not. Which is ironic, because Einstein got the Nobel Prize for his work on the photoelectric effect, but special theory of relativity and general theory of relativity he didn't get a Nobel Prize for.
What?
Even though if I were to show you the math right now for photoelectric effect versus special or general theory of relativity, you'd be like, wow, that's the theories of relativity are much more mathematically complex. But nonetheless, photoelectric effect is still impactful and amazing. It's just, it's funny. It's a little funny how straightforward it all breaks down. And the fact that Einstein was the first to see it just shows you sort of the elegance that he had. Mm-hmm. Everyone else just couldn't really, they kind of lost the forest from the trees. And he said, wait a minute, it's not that hard. And of course, it wasn't hard for him, right?
Yeah. Wow. So, now focusing on the path to become a great scientist in general words, what kind of opportunities and challenges people can face when they are studying a physics program like this? There are opportunities, or how are these opportunities?
Not quite. I understood the question. Like opportunities to grow as a scientist and contribute to the body of scientific knowledge of the human race. Yeah. Well, that really doesn't start to happen until graduate school. That's the whole purpose of graduate school, is to do original research and to contribute. And it's extremely difficult. I worked in a laboratory where we simulated, these dust grains in ultra high vacuum settings and stuff. And I had a joke with my lab partner. There was only me and one other person in the lab. And we had our advisors and so forth and support, but it was just us two. And I had a joke with him that it was like getting data from this lab, like meaningful data that we could analyze and write papers about, was like getting blood from a stone. Just because the whole purpose of an experiment is to produce as low an entropy environment as you possibly can. A controlled environment that does not evolve drastically with time. And to do that is extremely difficult. Like this room that we're sitting in right now, it's a lovely room. It's a quiet day on campus. It's Friday. It's comfortable. But it is extremely chaotic. There are air molecules bouncing off each other at astounding speeds. We are in an extremely high entropy environment right now. And go outside, forget about it. So to build an experiment, a meaningful experiment that truly contributes to the body of scientific knowledge of the human race is a tall order, to say the least.
Wow.
So, I guess to answer your question, I guess the point is to just learn as much as you can, absorb, and be prepared for the struggle. Enjoy the struggle. It's a rite of passage to be a scientist, to try things and for them not to work, be frustrated, and feel like you're really smart one day, and then feel like you're really stupid the next day. You got something way wrong.
Well,
And really, at the end of the day, that's what it feels like to be human. It's just when you're doing physics, and really any other science, that human feeling is so amplified. So, in that respect, I guess it really brings out the humanity. So, for example, after a long career as a graduate student wrestling with, these experiments in nature and a deeper understanding of nature and the principles of quantum mechanics, and then all of a sudden, you turn on the news and you see, some stupid political thing. It's sort of like, oh, please, please. As opposed to someone who doesn't study science, they might get wrapped up in that, and they probably will. When you climb the mountain of science, that intellectual mountain, you learn how to put that stuff in its place and go, that's noise. That's nothing but noise, and there's no logic there, and you're able to push it away, and stay humble yourself. I'm not trying to paint scientists as you got your nose up and everything, but you just have a filter really for nonsense, a very good filter for nonsense, not only with regard to other people and other activities, but your own nonsense as well. You really you're able to put yourself in a place when you're like, wait a minute, I'm being a jerk. All right, I'm too high up on my horse on this one. I've got to come down. So it's great. I don't remember the question. I hope I answered.
Yes, definitely.
I just feel like I'm rambling now. Yeah.
Don't worry, Professor. And now, to conclude this interview, what advice or tips would you offer to young people interested in physics or astrophysics like you for pursuing their passions?
Be brave. Science belongs to everyone. Maybe not everyone is cut out for it. Maybe not everyone wants to do it, but if you want to do it, do it. Be brave. Be courageous. Don't be afraid of it. And if you really want to do it, you can do it. And remember that just because maybe you're not the strongest math student now doesn't mean that you can't be later. So for example, with me, when I was studying math just for math's sake, I was not that into it. I was not very engaged. But when I went back to the community college and I was studying math to better understand physics, you better believe that I was paying attention to everything. I was very engaged in my math courses. I loved my math courses because I couldn't wait to take those tools and those toys and apply them to physics. And the same could be said if, someone wants to be an accountant and they want to be a money person, but then they want to take those mathematics and they want to be a business person, and the same thing can apply. But so point is just be brave, and you only get one go around here on this life, so you might as well do what you want to do and don't settle for anything less. Quite simple.
Thank you very much, Professor.
You're very welcome.
That's all the questions that I have for today. I really appreciate your time. Before you go, would you like to leave your sign here for
Yeah, sure.
special second season?
Should I take my mic off and yeah?
1 second. So we have 3 colors here.
Oh, this is the thing that all your guest signs?
Yes.
Oh, that's great. I love it. All right, sure thing.
Thank you again, Professor, for your time.
Thank you.